Okay, this is AQA AS Physics 2021, paper 1. As per usual, can't show the paper on screen sadly, otherwise AQA will get the whole channel deleted like they almost did in the past, but links to the paper and mark scheme are in the description. If you find this helpful, please leave a like and consider donating via the super thanks button to help me keep making these videos. 1.1, how many neutrons are in polonium-210? Well, we know that this is protons down the bottom, this is protons and neutrons. Therefore, the number of neutrons is just going to be 210 take away 84. That gives us 126. 1.2, bismuth 210, what's that, Bi? Surely, whatever. Decays to polonium 210. We know that's 84. And we've created a beta particle and, of course, an anti-electron neutrino. What are the mass number? Mass of an electron is essentially 0. Atomic number is -1. Therefore, just doing mass, that means that bismuth must have 83 protons. What has happened in between? Well, we know that a neutron has turned into a proton, and of course the electron as well, and the anti-electron neutrino, but we don't care about that really. So therefore, we say neutron has turned into proton, we could say decayed, so atomic number goes up by 1, but mass number unchanged, as same number of nucleons. 1.3, we have this graph here of kinetic energies, and it reaches 0 just before 1.2, I think. And this is kinetic energy in megaelectron volts. And this is the number of beta particles with that energy. Kinetic energies emitted from bismuth are analysed. They have a range of kinetic energies. Total energy released when each nucleus decays is 1.2 megaelectron volts. Explain how the data supports the hypothesis that a third particle is produced during beta minus. Well, it's because, like we said, max energy of beta particle is less than 1.2 megaelectron volts. Therefore, another particle must retain some energy. And of course, we know it's going to be an anti-electron neutrino. 1.4, why is an anti-electron neutrino rather than electron produced? Well, it's to do with conservation of lepton number. L equals 0 before decay, lepton number that is. L equals +1 for beta minus particle because it is an electron, and an electron is the OG lepton, so it has +1. Therefore, L of third particle is equal to -1, and we can say as nucleus L equals 0. Therefore, must be anti-electron neutrino. 1.5, we have this Feynman diagram. We have an unknown gauge boson, and we have an unknown particle being produced. What do we have here? We have an anti-electron neutrino, proton going in, and we have a positron coming out. Okay, so let's talk about charge first of all. We know that the charge of this going in, I'm going to say Q is charge, proton is +1, proton is +1, positron is +1, so therefore this particle must have a charge of 0. So we can say for Y, Q equals 0. Okay, so let's think about lepton number. Lepton number of an anti-electron neutrino is -1, -1 for the positron, so therefore this is going to have a lepton number of 0 as well. So it's going to be a baryon. Let's have a think about baryon number. Proton is +1. These are 0. So therefore it must be a baryon. So therefore you can probably see it's going to be a neutron. And we have this gauge boson going that way, as it were. And so we have a proton going in, and then it's turning into a neutron. It's almost like this gauge boson is taking away positive charge, but it's not doing that because it's going into it, as it were. That's the way the arrow is going. So therefore, we know it's going to be supplying a negative charge. So therefore, it should be a W- boson. Because this is a weak interaction, isn't it? There's charge involved. So therefore, it's not going to be Z0. It's either going to be W+ or W-, but it is giving that negative charge to the proton to turn it into a neutron. 1.6, the positron produced slows down and collides with a lepton in a molecule of water. Describe the process that occurs when a positron collides with this lepton. But here we have a particle and its antiparticle colliding together. So what's going to happen? It's annihilation. What does that do? Producing two photons, we could say, of equal energy, and we can say traveling in opposite directions in order for momentum to be conserved. 1.7, the range of the EM interaction is infinite. Here we have the range of strong and weak. That's interesting. We don't usually talk about the range of the weak force. Deduce whether the positron or the electron antineutrino is likely to travel the shorter distance in the tank before interacting. Ooh, not an easy question, this one. So let's have a think. A positron can interact by EM and weak force or interaction. Why not just say force? Whatever. Whereas an anti-electron neutrino, they call it an electron antineutrino, whatever, can only interact by the weak force. So I guess first things first, we can say therefore the positron can interact with electrons. It's not going to be electrons though, is it? Because it's going to annihilate them. But then I guess, okay, let's put electrons. I guess we're talking about annihilation as a possibility as well. But it can also interact with protons because protons have charge, not neutrons though. Electron neutrino can interact with only electrons. Therefore, will travel further before interacting. But they've also told us about the range as well. So I guess we could just add the one more point in here. Weak range is shorter. Therefore, we can say is less likely to get within this range to interact with particles. And we can say electrons, because that's the only thing that they're going to interact with. But I guess, hang on a minute, earlier we had a neutrino interacting with a proton, and that producing a positron and a neutron. So I'm a little bit confused about that one. I've got to be honest, stupid question, I'm moving on. Gosh, I hate particles. Right, diffraction grating, something a little bit better that we can actually do in the lab. We have our laser, we have a disc. Cheat is playing with the laser disc. State the path difference between light from adjacent slits when the light produced is a first order maximum on the screen. That, of course, is one wavelength. That's it. One ray has travelled one wavelength further and they've arrived in phase again. Explain how the light from diffraction grating forms a maximum screen. Ugh. When rays arrive in phase, they constructively interfere. Now, interfere. AQA seem to be reducing the number of words that you're allowed to use slowly but surely. So I would say interfere is absolutely fine, but they don't like that, so we're going to say superpose. Can't say superimpose. Therefore, intensity of light increases at those points. Yep, they say not interfere. Ugh. 2.3, we have the slit spacing for different generations of discs. Deduce the combination of disc and laser pointer that will produce the greatest number of interference maxima. So our equation is n lambda equals d sine theta. If we want the most orders, we want the smallest angle for each one. So therefore we're going to say sine theta is equal to n lambda over d. We're not concerned with n because we're just talking about any order, so therefore we're going to say sine theta is proportional to lambda over d. So if we want the smallest value of theta and therefore sine theta, we want the smallest wavelength and the biggest diffraction grating. So we're going to take our laser 8, because that has 4.45 times 10 to the minus 7 meters wavelength, and we're going to have our CD. Good old compact disc. Not your digital versatile disc. I wonder if you knew that's what that stood for. Not video. Okay, 2.4. I feel like I really messed this up last time, so let's have another go at it. So we're using CD and laser B. So therefore we know that D is equal to, what does it say? Wait, what are we using? We're using the CD, yeah. So it's 1.6 micrometers, so 1.6 times 10 to the minus 6 meters. Wavelength for B is 6.36 times 10 to the minus 7. I think that's where I might have gone wrong before. I might have used laser A instead. So the laser and the CD are in fixed positions. The laser beam is horizontal and incident. The height of the screen can be adjusted. Oh boy, okay. The screen has a diameter of that. The student predicts that using this arrangement, the greatest number of spots will be 3. Is the student correct? So we know that n lambda is equal to d sine theta. Now, let's have a think about this. So if it's right in the middle like that, so 15 centimeters either side, and we know that this is 15 centimeters here, then that means that we have an angle, or we can have an angle of 45 degrees here. So let's see what order we would get at 45 degrees, shall we? So we're looking for n, so n is equal to d sine theta over lambda, so that's going to be 1.6 times 10 to the minus 6 times by sine 45 divided by the wavelength, and I can just times by 7 on top, and so that gives us just times 10 to the 1, so therefore just 16 times that. Yeah, this is where I went wrong then. Right, so all of this hassle because I just chose the wrong laser. Good grief. So we'd end up with 1.78, let's say. It doesn't really matter. The point is that we will not get the second order appearing on there. So we would get the 0th order, we get 1 there, then we'd have 2 that would be off the screen, as it were, and then the second order the other side down here as well. There's the first order. So 0, 1, 2, 0, 1, 2. Now the question is, can we move this screen up or down to cover 4 of the spots? Well, let's find out. Let's find out what angle the second order is made at, shall we? So second order, and so that is going to be sine theta is equal to n lambda over d. So that's 2 times the wavelength divided by the distance, slit spacing. So again, let's just call that 16 on the bottom. 2 times 6.36 divided by 16, and then we're going to inverse sine that, and we end up with 52 degrees or 53 degrees, let's say. Now, question is, can we get 53 degrees? Well, let's have a think. So let's go with downwards. So we're going to say that's 53 degrees there. We know this is 15 centimeters. We're looking for this, and so this is obviously the opposite. This is the adjacent. So we're going to say, therefore, tan 53 is equal to the opposite over adjacent, which is 15. Therefore, the opposite is equal to 15 times tan 23 times tan 53. And we end up with, well, 19.9, let's just say 20 centimeters. So the question is then, if we move it down to here instead to get that second order, are we still going to have this first order showing up here? Well, let's check. So first order. So again, sine theta is equal to, well, just 1 times the wavelength divided by the distance. There we go, little shortcut there. And that gives us an angle of 23.4 degrees. So we're going to say then that the opposite this time is equal to 15 times tan of this angle. And we end up with just 6.5 centimeters. So yes, we can do this. So there's the CD, there's the laser light going in there, boop, 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 boop. And so therefore, if you move the screen to down like that, there's the center of the screen. We only have to go down 20 centimeters here to get to the second order. So that means our central max is going to be there, our 0th order. And so our first order that side, that just has to be 6.5 centimeters in there together. It makes less than 30 centimeters. So therefore, yes, we will not see 5 orders, but we will see 4. That's the answer. Not an easy question. Really trying to catch you out there. Caught me out. Maybe it didn't catch you out, but I guess this is what happens when you're not answering on the exam paper. That's my excuse anyway. So there we go. Finally fixed it. 3.1, we have a spacecraft, we have dust tail of comet, we have a mass of 1.1 times 10 to the minus 9 kilograms. That's our dust particle. And it has a speed of 5. I'm just going to call that 5,900 meters per second. Calculate the work done in bringing P to rest. Well, we know it's being stopped, so work done to stop is equal to, we know it's just an energy, don't we? Thus equal to the EK lost by particle. So that's equal to half mv squared. So that's half times 1.1 times 10 to the minus 9 times 5,900 squared. And that gives us, let's do that to 2 sig figs, or shall I just say 0.019 joules. And if it's work done, you can guarantee that we're going to have to use the work done equation. Yes, look at that. We're told we have moved a distance of 2.9 centimeters. Of course, we need to turn that into meters. So it's going to be 0.029 meters. And we're being asked to calculate the force. So work done, or energy, is equal to force times distance. Therefore, rearranging this, F is equal to energy divided by distance. So it's going to be our 0.019 divided by 0.029. I can cancel all those zeros. So we're going to have something that's slightly less than 1. It's going to be 0.66 newtons. 3.3, we have a graph of density against depth. Block is rectangular with an area of 8 centimeters squared. So what's this? The density is increasing with depth or thickness. Okay, what are we going to do with that? We'll check on that in a minute anyway. So let's find out the volume first. So there's going to be area times thickness. So that's going to be 8. Oh, but we have to turn that into meters cubed, don't we? Have to turn that into meters squared. Well, we have to divide by 100 twice. So it's going to be 8 times 10 to the minus 4 times the thickness. So that's 3 times 10 to the minus 2. And so that should give us 24 times 10 to the minus 6, or 2.4 times 10 to the minus 5 meters cubed. Right. We know the density is equal to mass divided by volume. So we can find out the mass from this, of course. So mass is equal to density times volume. But what density are we going to use? So I guess we could just find the average density. That's what they say anyway. So we're going to do the average density. So it starts off at 5, ends up at 50, and then we'll divide that by 2. That's the average density. I hate this question, it sucks. Then do times that by the volume. And that gives us 6.6 times 10 to the minus 4. This paper is not a good paper. I'm not liking this paper at all. Whew. 3.4 in another test, we have particle Q, right angle to the surface of the block, right. Q has the same mass, traveling at the same speed, so therefore it has the same kinetic energy. But Q is made from a less dense material. What? Oh my days, it just gets worse, doesn't it? So if same mass but lower density, volume is bigger. So if this is P, this is Q. And so therefore bigger area, we're going to say therefore will experience greater stopping or resistive force, therefore will not travel as far. Can we please have a proper question? Question 4, moments and stuff. Finally, this looks better. Well, where is it actually? We have D pulling down there. Oh boy, this looks complicated. Weight of this being 31. We have the guy holding on there, pulling out a funky angle to the vertical there. It's not perpendicular though, so I've got to be careful. And we have theta. And this is point X here. Whoa, okay, so, oh, they've already drawn it for us, that's nice. They've given us an angle as well, right? So that is 40 degrees there. Okay, so if that's 40 degrees there, we know that this is 40 degrees here as well, because of triangles. If you need to prove it to yourself, fine, but you should be able to see that. We're told that D is 53 newtons, so why the heck wouldn't you just put that on the flipping diagram to begin with? Oh my days, right. So we're being asked to find out the magnitude of u and also the angle theta. Oh, what? We're not actually doing this algebraically. They've asked us to draw a scale diagram. That sucks. Why? What's the point of having physics if we're just going to mess around with... Ugh. Whatever. Okay, fine. So we know that all of these forces are going to add up to 0 because it's in equilibrium, so we can draw a triangle of these forces. So we're going to draw 31. I think we can do, well, if we just do 3.1 centimeters. So 31 newtons going down, but then we have our 53 going down here. And so therefore that must mean that our unknown force is going back up here. That's going to be u, and then our angle is going to be that there. So when you draw this and then you measure it, you should end up with something like u being 79 newtons and theta being something like 25 degrees. Oh, I hate this paper. Gosh, this is the worst paper I've done in a while. 4.2 S and 31 newtons. We have X and we have Y. Do we care about Y? We're not even being asked to do calculations. We're just being... Discuss the differences. The athlete's left hand applies a force at Y. Okay. So of course that has to be upwards, doesn't it? He has to be holding it up like that. Discuss the differences between the magnitudes and directions of force U and force V applied in Y. Well, it should be similar, I guess, because we can say S is still perpendicular to beam. We can say that weight is still vertical, but now V, which is there, is vertical. We can say just from equilibrium, when it comes to forces, we can say that V must equal S plus the weight. We can say as weight acts now perpendicular to pole, moment is greater, therefore V must increase to maintain equilibrium. Oh my days, this paper is the worst. I feel like we haven't done any proper physics this whole paper. What is going on? 5.1, we have a momentum of 1 times 10 to the 7 Newton seconds. We've been asked to estimate the mass of the ship. Oh, what? So basically, how fast does a person walk as he's keeping up? 1 meter per second, surely. Therefore, mass is about 1 times 10 to the 7 kilograms. Yep, there we go. My days, what is this paper? Good grief. Again, no more calculations, just wordy nonsense. AQA, you've really royally messed up with this paper. What are you doing? Guess the virus hit them hard too. Okay, so how does the thrust of the propeller make it go forward? So propeller exerts force on water. Due to Newton's third law, water exerts equal and opposite force on propeller and therefore the ship. However, if speed is constant, ship must experience drag force that is equal to the thrust, therefore no resultant force, therefore no acceleration. And that is Newton's first law of motion. Guess we could invoke the second momentum as well, talking about in order to accelerate the water backwards, but I don't think we need to. Mark Scheme says we do, but I think that's really, really flipping mean. Moving on. I swear if I don't actually have any proper physics in the paper, I'm going to freak out. Hopefully electricity will save us. 5.3, introduction of a hull, drag reduction system, blah, 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 blah. System enables to save fuel. Explain why the system delivers this fuel saving. This is so weird. Ah, my days. I don't know. Let's have a think about this then. So, okay, so we can say drag decreases, as does thrust. Both of them are decreasing. Do you know what? I'm just going to look at the mark scheme for this one. This is ridiculous. This paper gets a fat 0. I guess we'd have to say that drag decreases more than thrust. I honestly can't be bothered. For constant momentum, drag equals thrust. Therefore, for lower drag, slower propeller speed required. Therefore, saves fuel. I am so done. We're not even done, actually. Guarantee you've never been so glad to see an electricity question in a paper, right? EMF of 5.3 volts. State what is meant by an EMF. Well, 5.30 joules of energy, because we know it's joules per coulomb. 5.3 joules of energy supplied to each coulomb of electrons, each coulomb of charge that passes through battery. 6.2, we have this set up here. So we have here 320 ohms. Our voltmeter is across that. We have our ammeter. We have 640. Okay, so we can probably see how the PD is going to be split across these. The reading on the voltmeter is 1.05 volts. When the that's it. Show the reading on the ammeter is probably, there's no internal resistance, so we don't need that at all. Right. Okay, so we're told that this is 1.05 volts. We know that the total EMF is 5.3 volts. So therefore, what does that mean we have over this resistor here? That's going to be 5.3 take away 1.05, so that is 4.25 volts. Okay, so we don't really know what's going on here. They haven't been really clear. I mean, they have said that the voltmeter is non-ideal, so therefore we know that the voltmeter is going to have some current flowing through it. So let's deal with this bit here. We have V, we have R, therefore we can find I from that. So V equals IR, therefore I is V divided by R. So that is 4.25 divided by 640, and that gives us 6.6 times 10 to the minus 3 amps, which is about 7 milliamps. 6.3, we're probably going to be asked to find the resistance of the voltmeter. Yes, we are. Shock horror. We need to find out the total resistance of this bit here. So V equals IR for this setup. We're looking for R. Therefore, that's going to be equal to V divided by I. So that's our 1.05 divided by 6.6 times 10 to the minus 3. And that gives us 159 ohms. Then we have to crack out a complicated equation. 1 over R total is equal to 1 over R1 plus 1 over R2. We're looking for R2, as it were. Therefore, let's do 1 over R total minus 1 over R1 is equal to 1 over R2. And so that's going to be equal to 1 over 159 minus 1 over 320. And so therefore, R2 ends up being 316 ohms. And there is a little bit of leeway there. Voltmeter is now connected across the battery terminals. Calculate the power dissipated in the voltmeter. So it's just going to be this. We don't care about this. The fact that it's a resistor, that is, well, I calculated it as 316 ohms. We know that the EMF is 5.3 volts. Therefore, we're going to be using V squared over R for our power calculation. So that's 5.3 squared divided by 316. That gives us 0.0 3 sig figs. Yeah, let's go to 3 sig figs, seeing that our data is all to 3 sig figs there, if I pop that in there. But 2 sig figs is fine as well. I think it should be 8, 9, whatever. They've gone to 2 sig figs. 6.5 voltmeter is now connected across the 640 ohm resistor. Oh. Still better than the previous questions though, but it's still not easy. And we said the resistance of this was, well, 316 ohms. That's what I had. Anyway, what are we being asked? Oh, we're being told that the PD shown was 2.1 volts. Explain whether some of these voltmeter readings does not equal the EMF of the battery. Oh, what a dumb question. Oh my days. It's because the ratio of PDs across both sets of resistors, that is the voltmeter and the resistor, changes, we can just say therefore total resistance changes, therefore so does current. What a dumb question. Right, AQA, you need to fire every single person who was involved in writing this paper. This is literally insane. 7.1, explain what is meant by modal dispersion in an optical fibre. It's when pulses spread out due to light rays dispersing and taking different paths, and therefore taking different times to travel along fibre. We can say it travels at different angles, entering at different angles as well, blah, blah, blah. Okay, we have this set up. What do we have here? Cladding, core, blah, blah, blah. We have a graph of sine theta r against frequency, where that's our theta r angle of refraction going in. This is 30 degrees. What are we being asked then? Transmit time between, okay, a single pulse, okay, transit time along, need to move this up, don't I? So we have a time of 5.225 times 10 to the minus 5 seconds. Okay, so the horizontal component of the velocity of the pulse is, oh, fine. We have the, oh, fine, we have the length, which is 10 kilometers, so 1 times 10 to the 4 meters. We're looking for a speed that is just the horizontal speed, and the length is in the same direction. So that's just going to be distance divided by time. So 10 kilometers divided by that time. We tidy up some powers of 10. This ends up being 9. So 1 times 10 to the 9 divided by 5.225. And that, sure enough, that gives me 1.91 times 10 to the 8 meters per second, slower than 3 times 10 to the 8, which is what we want. 7.3, frequency is 720 terahertz. So let's read off the graph. 720, that brings us over to a sine R of 0.3391, I do believe. Calculate the speed of blue light in the hour. Okay, so we need to find the refractive index of the material. So I always say start off with Snell's law. I think it's always worth it, just to avoid any mishaps. So we don't even need to find the angle because, well, we already have the sine of the angle, so that's cool. N1 is 1, theta 1 is 30, and sine theta 2 we said is 0.3391. Therefore, our refractive index is going to be sine 30 divided by sine of the angle of refraction, which we already have. Do we really need to go to 4 sig figs? I think we better had. So we end up with a refractive index of 1.474, just about, nearly 5. Let's go with 4. There is a bit of a shortcut with this question, but we'll do it properly. We know that refractive index is also equal to speed of light in air, vacuum, divided by speed of light in the medium. Therefore, swapping these two round, we're going to find that speed of light in the medium is going to be equal to 3 times 10 to the 8 divided by 1.474. And we can just do it as 3 to be perfectly honest. Let's do it to 3 sig figs, shall we? So 2.04 times 10 to the 8 meters per second. They ended up with 3, that's just rounding error. 7.4, 2 pulses of monochromatic light. Incident normally, so we have blue light and red light. Explain, with reference to refractive index, why the pulse of red light has a shorter transit time. So you should remember that red light diffracts more, but blue light refracts more. So we can say N for blue light greater than N for red light. Therefore, blue travels slower through fibre. So we have to write. Why is that 2 miles? That's weird. Whatever. Finally, get this blooming nightmare over. 7.5. 2 pulses identical to 7.4 are incident on the central axis and travel along its length. Okay, so they're just going pew, pew, both go in the same direction. However, the pulses are now incident on the air core boundary. So like that, and then like that. Okay, so just one reason why the difference in their transit times might not be the same. So obviously red is going to arrive sooner than blue, but that time difference between them is going to be different. It's because of, well, it's going to be because of this chromatic dispersion, we might say. Basically, they travel different distances. We don't know whether the blue light's going to travel further than the red light or vice versa. This has been absolutely the worst paper that I have ever experienced in my 12 years of teaching. AQA should be ashamed of themselves for producing such an incoherent, nonsensical paper that involves such little physics that it makes my brain hurt. If this is the way that AS is going, then it shouldn't exist. Having said that, I hope you found this helpful. Like I said, consider using the super thank buttons to help me keep making these videos. Join the Discord, plenty of helpful people there. Click on the card if you want to go to the playlist, which has all of the AS papers on. Good luck with your revision. I'll see you next time.